What up? We're going to continue on with talking about stereochemistry, which is kind of like the three-dimensional aspect of organic chemistry. By the way, some people say that I have a megalomania complex, but obviously I am obviously bigger than Jupiter right here, so I'm pretty much a big deal. The first thing that we'll do is we will review a couple of the concepts. First of all, keep in mind that we're talking about a subject known as chirality, or I guess more broadly, stereoisomerism. So we talked about the fact that anything that has a mirror image that is non-superimposable is considered a chiral compound. We also talked a little bit about the fact that if you have a mirror image that is superimposable, that is therefore something that is achiral. A couple of other things that we should review real quick. This idea of an asymmetric carbon. There we go. We got asymmetric carbon right there. So don't worry so much about this one. We're not going to talk about stereocenters so much, but I wanted to include this slide just because we have an example of two asymmetric, well, this one's actually a nitrogen, but this one is an asymmetric carbon. You'll notice that it's bonded to four different things, right? So if I'm that carbon and I go one atom out, I see an H in one spot, I see a Br in another, I see a CH2 in another, and a CH on another. So that's an example of a carbon that is bonded to four different things, otherwise known as an asymmetric carbon. So by way of review, we talked about the fact that in achiral compounds, the mirror image is actually superimposable. So this slide just kind of tries to represent that in, kind of two dimensions here. So we've got something which is a carbon that's not bonded to four different groups, so is not an asymmetric carbon. So these two groups right here, these two threes, they're the same. So you reflect it in a mirror plane, and it turns out that all you have to do to your mirror image is rotate it, and both of these structures are therefore superimposable, which means that these things are called an achiral compound. So that's something that I'm hoping that I can find you guys a pretty decent kind of a molecular manipulation program that you can kind of do these things on a computer. Normally in class we'd be playing with a bunch of model kits, and I'll try to kind of show you what the model kits look like when we get to the kind of the next set of video. Today's lecture, we're going to introduce a couple of new kind of vocabulary. For today, though, we're going to spend a lot of our time talking about something called an enantiomer. Enantiomers are very much related to that chirality topic. Enantiomers are two things that are related in that they have non-superimposable mirror images. So, in other words, any molecule that is chiral, right, or handed, must have, by definition, an enantiomer. In other words, the mirror image that is non-superimposable. So this particular set of slides includes this as an asymmetric carbon, right? So there's our asymmetric carbon represented right there. Keep in mind that that solid wedge means that Br is coming out at us, and that dashed wedge means that that H is kind of going behind the plane of the paper and away from us. And anything that is drawn as just a single line, that's actually in the plane of the paper. So what we have is, first of all, we know it's an asymmetric carbon because I've got four different groups, right? H, Br, CH3, and then CH2, CH3 are all different groups. So this guy is a chiral compound. It turns out the second that you say that, it means that it must have an enantiomeric pair, right? And so the enantiomeric compound is over here, and you'll notice that it is in fact its mirror image. And if we were to build this thing, which we'll be doing a whole bunch more on Wednesday, and try to overlap the two, we'd see that in fact those things are non-superimposable. So what does this have to do with real life? Well, it turns out that we're all made of a bunch of different enantiomeric centers. The thing about enantiomers is that their physical properties are exactly the same, right? And so here's just a couple of examples that if I had that enantiomer of one type from that last slide, and I had another vial that had the other enantiomer in it, it'd be really hard to tell them apart, right? Their melting points would be the same. The boiling points would be the same. Their densities would be the same. That's the N sub D is an index of refraction. Don't worry too much about that. Their heats of formation are the same. The only way that they're going to be different is their really odd interaction with plane polarized light. It turns out that if you have a pure enantiomer in a vial, it tends to rotate plane polarized light. So typical light is actually polarized in all 360 directions. So in other words, if you're staring at the sun like I am right now, the sun is putting out these photons that are going to my eye. Hey, there's my eye. And all of those things are polarized in 360 degrees. And it turns out I can pass that light through something called a plane polarized filter. Or, for instance, like polarized sunglasses, right? One of the things that it does is it reduces glare because it only lets a certain one of these planes through. And it turns out that if I pass that same plane polarized light through this thing called a through a solution that contains an enantiomer, what I'm going to see is some sort of rotation. So here's an example of the way a polarimeter actually works. Really the only thing that we need to concentrate on is the fact that there is this slight rotation of that plane polarized light. It's a really odd effect that was really surprising when it was first discovered. And so a lot of times, just to review some other kind of less important vocabulary words, if you have some sort of enantiomer that rotates light to the right, it's called dextrorotatory. Sometimes you'll see this plus sign written out in the front of compounds, and that's what it's referring to. There's also something called levorotatory, which is a minus, and then you can actually measure this optical rotation. The important thing that you need to know, you don't need to know much about which way a solution would rotate light one way or the other. The thing that you need to know is, first of all, the definition of an enantiomer. Right? An enantiomeric pair is something which is a pair of compounds that are the same in terms of their physical properties, with the exception of their ability to rotate plane polarized light in equal but opposite directions. And it's also a good idea for you to keep in mind that anything that is chiral, its mirror image is considered an enantiomer. Right? So that's called an enantiomeric pair. What we're going to eventually do is we're going to assign something called RNS configurations to these things. Really hard to do on a PowerPoint presentation, so I'm going to actually show you a couple of examples of assigning RNS. We should talk just real briefly about the fact that it's quite often the case that you have both enantiomers present in solution in a perfect 50-50 mix, and that thing is called a racemic mixture. Right? Or sometimes you'll hear it referred to as a racemate, right? And so here's an example of two different asymmetric carbons that are related in that they are enantiomeric compounds, right? So this guy is the enantiomer of this, and then that guy is the enantiomer of this. And so what you can notice is we got an asymmetric carbon. We notice that these two things are related and that they are non-superimposable mirror images of one another. And you'll notice something kind of interesting is that this guy rotates light 13.5 degrees to the right. This guy rotates light 13.5 degrees to the left, right? And so what happens is if you try to pass light through a racemic mixture, it ends up not actually rotating at all, because every time some of that plane polarized light interacts with this compound and gets turned to the right, it's just as likely to then hit this compound and rotate to the left. And so what you end up with is something that's called an optically inactive solution. So I'm going to make this a nice short video just so that you can kind of get those definitions down before we start to play around with actual organic molecules. So keep in mind the definition of enantiomer and also the definition of racemate.